Okay, this is going to be the first of a couple lectures on cytogenetics, or looking at chromosomes. So the objectives of this particular presentation include differentiating between reciprocal and Robertsonian translocations. So what's the difference between that? Recognize structural chromosomal abnormalities, including deletions, insertions, and translocations. Describe the difference between an inherited and acquired cytogenetic abnormality. I'm going to talk about it briefly, but mostly we're going to talk about the acquired in cancer. Explain the concept of non-disjunction. Recognize the method of cytogenetic nomenclature, including whole chromosome aneuploidies as well as partial chromosome deletions. So here's a chromosome, and really, as I've said before, it's a scaffold, and we've always had chromosomes, but we were able to start looking at them under the microscope in about 1959. We have 46 chromosomes, 2 of each pair, and they're tightly wound. So if you remember back from when you took molecular biology and other kinds of things, the chromosome, the DNA is wound around these proteins, these histone proteins, and then it's further wrapped around. And so, like I said, this chromosome is a scaffold, and the two sides are held, the two chromosomes are held together at the middle by the the two chromatids are held by the centromere. So chromosome abnormalities, there are inherited chromosomal abnormalities and acquired. Inherited is what was in the egg and sperm that made that baby. Acquired are changes that occur, losses of genetic material, extra chromosomes, and things that happen in individual cells. The acquired we're going to talk about in cancer cytogenetics, which is actually far more used than routine nowadays, but I just wanted to mention that. So why would you look at someone's chromosomes? One is prenatal. Prenatal diagnosis, advanced maternal age, high screening risks, or an anomaly in the fetus. I have another lecture for this particular case on prenatal, and we'll talk about that more. Multiple pregnancy losses. Have these two parents had multiple pregnancy losses? And a family history of mental retardation or cognitive delays, birth defects, and or a chromosomal abnormality. In pediatrics, a child with developmental delay, multiple congenital anomalies, multiple birth defects, a problem with fingers and toes and legs and a heart and kidneys. Cancer. Again, most of what we're going to talk about in this, we're going to be talking about developmental cytogenetics, which is the first two. So, but cancer are acquired chromosomal abnormalities that cause that cancer cells to go crazy. And again, we're not going to talk about this. I just want to put out that seed for when we get to oncology or hematology, actually. So tissues, anything with a nucleus. So blood cells, the T lymphocytes, and normally your T lymphocytes, unless you have cancer, do not divide in the periphery. So you have to add a chemical called phytohemagglutinin, or PHA, to cause them to start dividing. Skin or muscle, placenta. The placenta has nucleus. Products of conception. When a woman loses a pregnancy, whatever comes out, we can culture. And then, again, tumors, either bone marrow biopsy or solid. Amniotic fluid is actually skin cells from the baby that slough off that we can test. We're going to talk about that more in prenatal testing. And then chorionic villi is a piece of the placenta. So it's really the placenta. So here is what chromosomes look like when I drop them. I've cultured them for like 48 hours, and I drop them on a slide. And we actually add a hypotonic solution to burst open the cells so that the chromosomes spread very nicely. And here's a cell that didn't open up. And then we actually band them. We add chemicals, in this case trypsin, to, so that we can spread them nicely. And here, I mean, they're like, here's a chromosome 22, here's another 22, here's a chromosome 21, and here's the other 21. So they're very random when they fall down. But then we put them in size order. And this chromosomes put in size order is known as a karyotype. Now, again, we have 46 chromosomes, 2 of each pair. Girls have 2 X's, boys have an X and a Y. And so here you might notice this Y is a lot smaller than the X, and we're going to talk about this a little bit later when we talk about the sex chromosomes. But females, because they have more genetic material, actually shut off one of their X's. The chromosomes with the most genetic material, the most genes, and only about 40 to 60% of any given chromosome has material that we know of that's inherited. So there might be some other factors that we're not, but as far as actually Mendelian inherited genes, the chromosomes with the most genetic material is actually 1 in X, 2, 3, and 4, 5, and then the next one is, that's right, you guessed it, 19. This little teeny chromosome has more genetic material than a lot of these. The chromosome with the least amount of genetic material is 21. It's probably why it's the most likely, it's not the most likely to result in a trisomy. It's most likely to result in a live born from a trisomy. Okay, so this is actually the smallest human chromosome, and it has the least amount of genetic material, which allows it to survive when there's an extra copy. So let's go over the anatomy of the chromosome. So the centromere attaches the long and short arm. And the P arm, P stands for petite in France, and a lot of the early nomenclature was done in France. So P stands for petite, and Q is the next letter in the alphabet. So the short arm is the P arm, and the long arm is the Q arm. The centromere is the middle, and the telomere is the end. And sometimes you'll read things about telomeres. There's a lot of repetitive DNA at the ends of the telomeres, and people that seem to have longer telomeres seem to live longer. I'm not going to really be talking about that. I just wanted to describe what a telomere was. So nomenclature. If normally 46XX or 46XY, if there's an additional chromosome, you write which one it is. So in Down syndrome, 47 instead of 46, XX or XY, comment, and which is the extra one. So why is it 47 instead of 46 plus 21? So 47 XX or XY plus 21. If there's a deletion, what we show is which arm. So deletion, DEL, and then this is chromosome 5. If it said 14.2, 14.2, everything distal to this is missing. So if you just see one little, like, one number, everything is missing. An interstitial deletion is a deletion in the middle. So deletion, chromosome 5, P11.2, 11.2 to 12.3. So this little piece here is missing. When we first started doing cytogenetics, you would never see this because it's very difficult to see this. This is like a white part. How are we going to notice that this is a little closer than it should be? But now when we get to the molecular techniques, we're better able to see this. But this, if you just see the one number, it's a terminal deletion. And there's actually a disorder known as 5p deletion or Credit syndrome caused by that. Maybe there's a hot spot. I don't know why, we seem to lose that. So gene location, the genes are located on the chromosomes using the same method in nomenclature. So first we started with cytogenetics, then we used linkage to determine where genes were. And so, for instance, the gene for cystic fibrosis, which you learned about last year, is on the long arm of chromosome 7, 7q31.2. And here's our little piece, here's our gene that codes for a protein that sits in the cell membrane and transports chloride. So the same kind of nomenclature, we use the same P and Q arm and things like that because the original genes were located using linkage analysis. We do a different method now. I'm just giving you the historical, perspective. Aneuploidies are the most common cause of pregnancy loss. So we're going to talk about this more when we get to the prenatal lecture, but 50% of all first trimester pregnancy losses have a chromosomal abnormality. In most cases, it's a structural, like an extra missing chromosome. Women over the age of 35, it drops to 1 in 50, and the vast majority are still numerical, but they can be structural, like translocations, which I'm going to talk about in a second. And live births, it actually goes down to 60% because a lot of these severe things are lost during the pregnancy. So chromosome aneuploidy, a whole extra chromosome, includes trisomy 21, trisomy 18, trisomy 13, 45X. The sex chromosome aneuploidies like 47XXY, known as Klinefelters, 4p minus and 5p minus. And the reason I bring these up is these were historically described as disorders that we could actually see when we started looking at chromosomes. And when I get into molecular cytogenetics, there's just a lot more. So when we make a baby, we have a meiosis where we divide. We don't give the baby 46 chromosomes. We only give 23. So we divide our chromosomes in half from mom, half from dad. The baby gets back to 46. So 23 in the egg, 23 in the sperm. If the dad gives an X because mom has an X, it's a girl. If he brings in a Y, it's a boy. So the father determines the sex of the baby. Sometimes mistakes happen. And if you think about it, there are 23 different places you can make a mistake. Most of the time, you end up with a pregnancy loss and you don't, end up with anything. But here we have this individual divides their chromosomes equally. I'm only showing 2 because it's too confusing if I showed you 23. And this individual has non-disjunction. So this is, let's call this chromosome 1 and chromosome 2. Instead of dividing equally in meiosis 1, both chromosome 1s go to one side, and then so one parent donates 2 copies of chromosome 1 and the other donates 1. And so this baby has 3 copies and 2 of all the rest of them. And in this cell, if this was used for fertilization, this would result in just a single copy. The only disorder that's compatible with life with a missing chromosome is Turner syndrome, which is 45X. I will talk about that in a separate lecture. But almost all monosomies are lethal, and most trisomies are lethal, with the exception of trisomy 13, 18, and 21. They happen, they just usually result in products of conception or pregnancy loss. So, as I said, 50% of first trimester pregnancy losses have abnormal chromosomes, and so we recommend chromosome analysis in anyone that's had 2 or 3 first trimester pregnancy losses. But it's really important to separate the tissue, because if every time you do a product of conception is 46XX, you probably didn't do it right. Okay, I'm going to talk about the clinical characteristics of Down syndrome in a later lecture, but it's actually in probably the next rotation, this next thing. But types of chromosomal abnormalities. Down syndrome, when I see a baby, so Down syndrome was described as a disorder in 1860. We didn't know about chromosomes, as I said, till 1959. So you go into the nursery and you see a baby and you make a clinical diagnosis of Down syndrome. 90 to 95% of the time when we look at chromosomes, there'll be an extra copy, and that's because of non-disjunction, because an extra copy occurred when the egg or sperm was being made. 2 to 4% are mosaic. That means that the conception started with 47 XX or XY plus 21, but in early embryonic development, one of those extra copies of the 21 is lost. And now, if only 5% of the baby's cells have plus 21, they'll probably have a milder phenotype. But if it's like 80% plus 21 and 20% not, it may or may not affect the phenotype. My biggest problem in life is Dr. Google, because parents get on the internet and they're like, oh, maybe even if it's Downs, it's a mosaic. And really, I try to discourage that particular hope, because there's a wide variety of outcomes in children with Down syndrome. Again, I'm going to talk about that in the next actually, I think it's life cycles when we talk about dysmorphology, but so you won't be responsible to know the phenotype now. But the last is translocation, and this is actually important for the cytogenetics. So there's a rearrangement of the chromosomes, and it does not affect the phenotype. It only affects the risk for it to happen again. But again, it's a relatively rare cause of Down syndrome. But here here's actually a copy of 21. It's attached to 14, and here's 2 more. So this is known as a Robertsonian translocation. And so what happens is about 1% of the population carries a translocation. If one individual has, instead of 46 chromosomes, 45, they have a 14, a 21, but a 14 and a 21 together. The short arms of these chromosomes are known as acrocentric chromosomes, are repetitive DNA. Losing them is not a big deal, and because they're repetitive and they interact with each other, the chance of a translocation actually increases. So this individual is a balanced carrier, but only has 45 chromosomes, but this one really counts for 2. The problem is when we're dividing, and if you remember from meiosis, there has to be that special part when you cross over. How do they do this? And they make this trivalent so that they can cross over. Now, if the 1421 goes to one cell and the 14 and the 21 go to the other, then when we fertilize, we get normal or a carrier just like the parent. Yay! But what if the 1421 migrates with the 21, leaving the 14 alone, or the 1421 migrates with the 14, leaving the 21 alone? When this is fertilized with the other parent's normal chromosomes, in this case we have 2 14s and 3 21s, Down syndrome, 2 14s and 1 21, lethal, 3 14s and 2 21s, lethal, or 1 14 and 2 21s, lethal. So of these possibilities, this is the only one that's compatible with life. So you'd say, well, why is it like, you know, if a parent's a 1421 translocation, why is it only 15% chance that they could have a baby with Down syndrome? And that's actually the risk. It's because a lot of these are not compatible with life. So here's just, here's our normal chromosome, the derivative chromosome. So normal segregation, we divide our chromosomes equally. Here's the light blue is the 14 and the dark blue is the 21. But again, when we have our 14, 21 together, we have to make this trivalent. So if we, you know, if our 14 goes with our 21, and the 14, 21 goes together, when that's fertilized, that's just fine. But if we have, if the 14 goes with the 21, this ends up with Down syndrome, and this one ends up being lethal. So the risk for carrying a Robertsonian translocation. If a parent has a 1421 translocation, there's a 5 to 15% chance of having a baby with Down syndrome. As I said, you'd think, why isn't it like much higher than that? Because many of these are lethal. If the baby is born with Down syndrome, however, and I do chromosomes and they have a 1421 translocation, there's only a 50% chance it came from a parent. It actually could have been a de novo event in the egg or sperm that made the baby. So the next step would be to look at the parent's chromosomes. And then if one of them did carry it, they're at increased risk over the general population to have another baby with Down syndrome. Now, that's a Robertsonian translocation, and that's a special translocation between 2 acrocentric chromosomes. We can have rearrangements between any 2 chromosomes. So let's call this, again, the blue is 1 and the gray is 2. What if part of 2 is on 1 and part of 1 is on 2? This can occur, as I said, with any 2 chromosomes. So if when we're dividing our chromosomes, the individual with the normal karyotype, fine, but this person could give his normal blue and his normal gray, and when that fertilizes, the baby's normal just like the parent. Or it gives the blue with part of gray on it and the gray with part of blue on it. Well, when you add this all up, you get 100%, so that's great. But what happens if the chromosome with the normal blue goes with this chromosome that has gray and part of blue on it? We're missing part of this gray chromosome, and we have extra. So we have extra 1 and missing 2, and here we have extra 2 and missing 1. So both of these are deletion duplications. To be honest, the larger the piece that's translocated, that you either end up with a miscarriage or a balanced or normal baby. Little teeny pieces can result in a child with multiple anomalies. So this is something that we look at with the chromosomes when we have a baby with the multiple anomalies. When we see that there's a translocation, again, we want to look back at the parents to determine. The other reason that we would look at the parents is if they've had multiple pregnancy losses. Sometimes it's such a large piece, you just don't end up with a viable baby. So reciprocal translocations, as I said, can occur between any two chromosomes, 1 and 3, 3 and 8, anything. While the individual with the balance rearrangement is normal, there's a risk in most cases. Occasionally there's like a gene interrupted, but in most cases they're normal. But there's a risk that they won't separate correctly during meiosis. It is possible, like I said, for a gene to be interrupted. When there's an imbalance in genetic material, there's a risk of either pregnancy loss or a baby with multiple anomalies. About 1% of the population carries some type of translocation. Some of these are Robertsonian, which are actually the most common. The other are reciprocal. And all these translocations, reciprocal and Robertsonian, can occur in either mom or dad. So it could be either parent. It's not just the mom. And so when we have to do this, we have to look at both parents, not just one. So a baby is born and has chromosome analysis that indicates 47 XY translocation 1421 plus 21. So if somebody has a 1421, they actually have 45 chromosomes. So if they have 46 and it's telling you there's an extra copy here, remember I said 47 XX, and then we should have 46, but it's telling you what's the extra. So the diagnosis is, so XY is a boy, and when we see this, it is a male with Down syndrome. So this may be kind of like a question you might get on your exam. So 40, if it was 45 XY translocation 1421, it would be a normal male. So that concludes this presentation.